Okay, this is Chapter 2, Section 3, Applying Deductive Reasoning. We talked about inductive reasoning previously, and that's using patterns to make a conjecture, educated guess, or a conclusion. Deductive reasoning is a little bit different. Deductive reasoning um, in deductive reasoning, uh, we're not looking at patterns. In deductive reasoning, we're making a formal argument. We're going to use facts. We're going to use definitions. Um, to form we're going to use laws of logic. We're going to use all of that in a formal argument. We're using facts, definitions, we're using laws of logic in a formal argument to reach a conclusion. Or conjecture. Alright, so two laws of logic. The first law of logic that they talk about is the law of detachment. And the law of detachment says in a conditional, if the hypotenuse is true, then the conclusion is true. If the hypotenuse is true, then the conclusion is true. That is the law of detachment. And the law of detachment, we're given a conditional. After we're given the conditional, we're told, okay, the the hypotenuse must be true, and if the hypotenuse must be true, then the conclusion of our conditional must be true. So, for example, let's do a conditional. Um, if I study, then I will get an A. If I will study, then I will get an A. That's my conditional. Then I'll get the secondary statement saying, um, I studied last night, just making this up. Alright, so since I studied last night, then what can I conclude? I can conclude that I will get an A. Because I studied last night confirmed that my hypothesis of my conditional, remember anything after if, I studied, is true. So if I studied is true, then I will get an A is also true. Therefore, I can conclude that I will get an A. That is the law of attachment. The law of syllogism. says that a couple things. Thing number one, uh, we have these notations for things. Um, P means hypothesis. We'll talk actually about this in real soon. Q is conclusion. Most of the time. Um, R can also be considered a conclusion, and this is most of the time. In the case of syllogism, though, we're dealing with two different conditionals where two of them are one the conclusion and one is the hypothesis of the other. But in most logic notation, most of the time, P is the hypothesis and Q is the conclusion. Those are the two things I want you to take away from that. So what they're telling me for law of syllogism, and it says this: if the hypothesis Q then conclusion Q. If hypothesis Q, oops, I wrote Q twice. I hate P and Q because I flip my P's and my Q's. If hypothesis Q then conclusion R, so if I have an hypothesis P, then I have the conclusion Q. If I have the hypothesis Q, then I have conclusion R. What the law of syllogism says is that I can combine these two conditionals and notice that the conclusion of one of the conditionals, Q, is the same as the hypothesis of the other. So they kind of cancel each other out. This only works if the conclusion of one conditional is identical to the, well, not identical, so the same as the conclusion or the hypothesis of the other conditional. I repeat, this only works when the conclusion of one conditional is the same as the hypothesis of the other. So what can we conclude? We can conclude, this is our third conditional, that if hypothesis P, so the hypothesis of the first conditional, then conclusion R of the second conditional. So we call this conditional 1, conditional 2, conditional 3. All right, we have the hypothesis of the first conclusion, the hypothesis of the first conditional, then the conclusion of the first conditional. The conclusion of the first conditional is the same as the hypothesis of the second conditional. And if the hypothesis of the second conditional leads to the conclusion of the second conditional, I can cancel these guys out. That can go, and that can go. And what's left over is the hypothesis of the first conditional and the conclusion of the second conditional. I can combine those to create a third condition, a third conditional. And that's the law of syllogism. We'll talk about logic notation in a second. Okay, so an example of law of detachment, they give us 2. Here they say, if two segments have the same length, then they are congruent. You know that BC is equal to XY. Here's my conditional. It says, if two segments have the same length, then they are congruent. That is my conditional. If two segments have the same length, then they are congruent. Okay, that's our conditional. What are we told? We're told BC equals XY. This tells me that the hypothesis is true. So since the hypothesis is true, what can I conclude? I can conclude, or I can say, that the conclusion is true. Then I can say that, okay, if the hypothesis is true, then the conclusion is true, then I can say that BC is congruent to XY. Why? Because I know that they're equal, and the conditional says that if they're equal, then they are congruent. Law of detachment. It's sort of it's kind of like, okay, that kind of like why, but it kind of helps us move along in our formal arguments with proof that if we know one thing is true, then we conclude the other thing. This one says Barry goes to the movies every Friday and Saturday. Today is Friday. So saying that today is Friday tells me that the hypothesis is true. If Mary goes to the movies every Friday, if it's Friday or Saturday night, then Mary's going to go to the movies, right? That would be basically our conditional. It says today is Friday. So if today is Friday, then we can make the conclusion that Mary is at the movies. Or she will go to the movies tonight. Law syllogism. An example that they have here. It says if Rick takes chemistry this year, then Jesse will be Rick's lab partner. So that's the first conditional. Rick, I'm going to say R for Rick, takes chemistry. Then we can say Jesse will be Rick's lab partner. Lab partner. That's the first conditional. Second conditional says if Jesse is Rick's lab partner, so if Jesse is Rick's lab partner, then like we're getting a yay. So then the third conditional I can say, notice that the hypotenuse, the conclusion of the first conditional, Jesse will be Rick's lab partner, is the same as the hypotenuse of the second conditional. Jesse is Rick's lab partner, so they can go bye-bye. Well, actually, we need it then. That can go bye-bye. So we can say if Rick takes chemistry, and Rick will get an A. Yay. Okay. Again, the conclusion of one condition is the same as the hypothesis of the second one, so we can form a third one, which includes the hypotenuse of the first conditional and the conclusion of the second. That is law syllogism. All right. So for the guided practice, there's a lot of writing in this, so I'm just going to look at the focus more on to the left, the picture. So it says that if we have an angle that's between 90 and 180 degrees, which is angle R, then angle R is obtuse. So if angle R is in between 90 and 180 degrees, angle R is obtuse. And then we're told that angle R is 155. Well, 155 is between 180 and 90, so then we can say that angle R is obtuse. That's what we can conclude. Angle R is obtuse. Number 2 says if Janelle gets a job, then she can afford a car. If Janelle can afford a car, then she will drive to school. So using a law of syllogism, you can conclude, since the conclusion of the first conditional is the same as the hypothesis of the second conditional, they can go bye-bye. Then I can write a third conditional, and that one says if Janelle gets a job, then she will drive to school, using the law of syllogism. Number 3 is to ask you to say which one of the laws of logic is illustrated. Number 3, if you get an A or better on a math test, then you can go to the movies. If you go to the movies, then you can watch your favorite actor. If you get an A or better on your math test, then you can watch your favorite actor. That is the law of syllogism. The conclusion of the first conditional is the same as the hypothesis of the second conditional. They cancel out. Therefore, you can write a third conditional, which is the hypothesis of the first conditional and the conclusion of the second conditional. If x is greater than 12, then x plus 9 is greater than 20. The value of x is 14. So then what we can conclude is that x plus 9 is greater than 20. We have our conditional, and then we're given a statement that says that the hypothesis is true. X 14 is greater than 12. So since 14 is greater than 12, we know that x plus 9 is greater than 20. This is the law of detachment. Alright, so the next two examples is like telling the difference between inductive and deductive. Is the stuff you guys can do. It's not that difficult. Alright, so symbolic notation. Alright, P equals hypotenuse. Q equals conclusion. And then we have the arrow. And the arrow sort of is like our if and then. So when we do a conditional, and we also have a biconditional, if and only if, which is the double arrow. So this means if and then, because I'm going to write this a lot in class. And this means if and only if for a biconditional. Okay, those are our conditions. P is the hypotenuse, Q is the conclusion. The arrow going to the right is if and only if. And oh, I'm missing one. Let's see. Do this. Let's write smaller. P is the hypotenuse. Q is the conclusion. Look at that. I can write small. Then we have this little squiggly line. So this little squiggly line means the negation or not. So you can think of it as not, or you can think of it as negation. Okay. So, conditional. If P then Q. So but we're not going to do that because we'll just write if P then Q. That is your conditional. Then we have the converse. And the converse, remember, flips the order. And converse is if Q then P. If Q then P. And then we have the inverse, which is the negation. And the inverse is going to be if not P, then not Q. And then we have the contrapositive, which is the negation and the inverse. Which is if not Q, then not P. And then lastly we have the biconditional. And that is if not P, no, I'm sorry, biconditional is P if and only if Q. And that's the double arrow, P if and only if Q. Okay, so conditional, if P then Q. Converse, if Q then P. Inverse, if not P then not Q. Contrapositive, if not Q then not P. And then biconditional, P if and only if Q. And they have examples of angles and stuff with 90 degrees, and I don't want to get into that. Just know those are the symbolic notations. So I'm going to do this a lot with the ifs and thens, especially with the arrow and P's and Q's. That will reoccur quite a bit. Okay, 2-4. 2-4 is sort of a silly chapter, but they do give us a whole bunch of postulates. So we've already talked about the first four. And the first four says, we talked about the ruler postulate, segment addition, protractor, angle addition postulate. Remember that postulates are rules and conditions that we don't have to prove. Rules and conditions that we don't have to prove. Soon we're going to start talking about theorems. And theorems are rules that we do have to prove. And that's coming down the pike. Or rules that could be proved. So postulate number 5. And it says this: through any 2 points, there exists one line. So I have point A. I have point B. And I have point C. And what postulate number 5 says is that if I want to put a line between point A and B, I can only put one line. If I want to put a line between A and C, I can only put one line. And one line only. Through any 2 points, there is exactly one line. Postulate 6 says a line contains at least 2 points. A line can be is maintained by infinitely many points, but the smallest amount of number, the smallest number of points that a line can possibly have has to be 2. It has to have at least 2 points to form a line. That's postulate 6. I'm not going to write them down. They're right there. You can pretty much copy it when you see it. Postulate 7. If two lines intersect, they intersect at exactly 1 point. So here's postulate 7. I have a line L. I have a line M. Two lines will always intersect only at 1 point. Call that point P. Two lines intersect to form 1 point. Exactly 1 point. Notice that the word is exactly, meaning one and only 1 point. There's not going to be a case where I have a line intersect, two lines intersect and they form 2, 3, 4, 5 points. They can only intersect and form exactly 1 point. Postulate 8. Through any three non-collinear points, there exists exactly one plane. In order for this to work, there has to be non-collinear, right? And that guy forms one plane. One plane. All right, 3 points, plane P, forms exactly one plane, and they have to be non-collinear. Postulate 9. A plane contains at least 3 non-collinear points. Now, a plane is comprised of infinitely many lines, which is comprised of infinitely many points. But in order to say that I have a plane, I need at least 3. At least 3 non-collinear points. Postulate 10. If 2 points lie in a plane, then that line containing that point also lies in the plane. So line A and B, or I'm sorry, points A and B are in plane P here. I can say that since those 2 points are in the plane, I can say that line L is also in the plane, the line that contains those 2 points. If point A and C are in the plane, then I can say that the line that contains A and C, line M, is also in the plane P. So if the 2 points are in the plane, then the line that contains those 2 points are also in the plane. Postulate number 10. Postulate number 11. If 2 planes intersect, they intersect to form a line. 2 planes intersect to form a line. I can't draw 2 planes intersecting, so I want to give it a try. But know that when they do, they form a line. Okay. So there's like drawings, and you can make conclusions off of those drawings. The first drawing says here, or diagrams, 2 lines intersect, then they form a point. And this one says, here's the drawing of the planes. If 2 planes intersect, notice that those planes intersect, they form a line right across their intersection point. This one says to identify the postulate, so use the picture in example 2. For guided practice 1, it says use a diagram in example 2. Which postulate allows you to say that the intersection of the plane P and Q forms a line? That is postulate number 11, which says 2 planes form a line. It says write examples of postulate 5, 6, and 7. So postulate 5 says through any 2 points there exists one line. Postulate 6, the line contains at least 2 points. So if we look at this picture, postulate 5 says through any 2 points there exists only one line. So if we look at B and A, we can say that B and A there only exists one line, which is line N. That's an example. And then postulate number 6 says a line contains at least 2 points. Again, we can say that is also B and A. The line N contains at least 2 points, B and A. So that satisfies both conditions, postulate 5 and 6. Postulate 7, it says two lines intersect. They intersect at exactly 1 point. If we look at line M and line N, they intersect to form point A. So that satisfies postulate number 7. When you get these diagrams, there's going to be things that you can see, or you can prove or assume based off of the drawing, and there's going to be things that you can't. And they give you a bunch of things that shows that case. We can see that AHB and BHD are a linear pair. So AHB, which is this guy, AHB, and the other one is, which one? BHD. They form a linear pair. So if I was to draw it, you might not be able to see it. It looks like this. So this is A H and B, and then there's also D over here, and then BHD. They form a linear pair because if I add these two guys up, they're adjacent angles that sum up to 180. So that we can assume that based off the drawing because it's in the drawing itself. So we're gonna be able to make assumptions from drawings. I'm not gonna get into all of these. I'll just go through one example. You guys can look back on it yourself. We can also assume that we can assume that G, F, and E are collinear. G, F, and E doesn't have a line through them. They don't show a line through them. So since they don't actually physically have a line being drawn through them, I can't assume that they're collinear. It kind of looks like they are, but I don't have enough information based off the drawing to say that they do. So it's basically utilizing the information from the drawing to draw a type of conclusion from the drawing. A perpendicular line by conditional here. It says if a line is perpendicular to the plane if and only if the line intersects the plane in a point and is perpendicular to every line in the plane. So basically what they're saying is this. I have a line from this figure, line T. Line T is intersecting plane A, forming a perpendicular intersection at that point. If the line is perpendicular to the plane, not only is it perpendicular to the plane at that point, but it's also perpendicular to every line in that plane, because remember, a plane is comprised of lines. So if I have a line that's perpendicular to the plane, it's going to be perpendicular to every single line in that plane, because a plane is comprised of lines. At the point where it intersects. Okay. Again, I don't. Guided practice really gives you like examples of referring back to the figure and seeing what conclusions can you make from the figure. This one says to refer back to example 3. If the given information PW and QW are congruent, how can you indicate that in a graph? So we look at this picture here. They want to know what can I do to make this PW, PQ look congruent. So we have an intersection at W. This is a line segment P, line segment Q. It's cutting TV in half. So, and it shows that these two guys are congruent. WV, WT. They want to know what can I do to show that other segment congruent. I would have to put two markings. And once I put two markings here, then I can say that PW is congruent to WQ according to this drawing here. It says name a pair of supplementary angles in the diagram. So if I refer back to example 3, a pair of supplementary angles, I can say TWP and PWV, they're supplementary. Because they are a linear pair, I can say TWQ and QWV, they're supplementary. I can say PWV and VWQ. I can say PWT and TWQ. These are all linear pairs, and therefore they're all supplementary, based off of the drawing. In a diagram though, assume plane S intersects T at line BC. Can you assume that? Can you assume that? An example 4. So we have plane S and intersects plane T. Notice this line that's formed. We have that line that, remember, two planes form a line. And then we have B and C. B and C is in that line that's in that intersection line. So we can say and conclude that line BC is formed by the intersection of plane T and plane S. And then number 6 says, how can you know that AB is perpendicular to BC? So line AB is perpendicular to plane S because it shows that perpendicular symbol to the plane. And the perpendicular by condition that we just stated said that if a line is perpendicular to the plane, it's also perpendicular to every line in that plane. So from that perpendicular by conditional, we can say that line AB is perpendicular to line BC. Okay, and that's those two sections. Hope you have a great rest of your day.